invertendo, alternando, tornado. One of these addos doesn't really fit. So, without further ado, you should get rid of the tornado. But that leaves a large empty space that needs to be filled. Fill that with this componendo. It's another useful theorem that you should know ando. Excuse me, please. Let me tell you how we get it. As always, we start off with this. If you don't mind, we will equate these ratios in the form of fractions. Now, add 1 to both sides. Simplify and you end up with this. Of course, these can be written back as ratios again. This new form is actually called the Theorem of Componento. But how will you remember it? Adding 1 and then solving all this sounds like a hassle. Well, just to help you memorize it, note that it appears as if we have added the denominator of each fraction in the numerator. And the second part of it can be memorized as if we added the numerator of each fraction in the denominator. Easy peasy now? Let's check an example to see how we apply it. These two ratios are given and we need to get this part. First, write these ratios as fractions. Now, remember the shortcut to apply the componendo theorem? Add the denominator to the numerator in each fraction, like this. Simplify this to get m plus n plus 3 upon n, and at this side we have p plus q minus 2 upon q minus 2. If you convert it into a ratio, you will see that you have proven what you had to. Now, instead of adding 1 to both sides, what if we subtract 1? Well, that leads us to the next theorem known as dividendo. Example number 4 will show you how to apply it. We have to take these two ratios and get this. Start by converting the ratio form into fractions. Now, the shortcut to apply the dividendo theorem is to subtract the denominator from the numerator on each side. Then, just simplify the fractions and change the final results back to ratios. Compare this with what you had to prove. You've done it! Now that we have a handful of componendo and dividendo, why don't we combine them to get something like componendo-dividendo? And it too is actually a theorem. By applying both the componendo and dividendo theorems together to our old buddy, we get a componendo-dividendo theorem that looks like this. Now, we'll jump quickly to an example to see its application. There are two ratios given, m to n equal to p to q, and we have to prove this. Start by changing these two fractions like we always do. At this point, notice that our required ratios have 3 with the m and p and 7 attached to the n and q. So, just multiply 3 upon 7 on both sides of the equation to get 3 with m and p, while 7 with n and q. Now, if this is a, b, c and d, then to apply the componendo-dividendo theorem, we first need ab with a plus sign here and with a minus sign here. Since 3m is our a and 7n is b for us, so we will write them with a plus sign and then with a minus sign. The same is the case for c and d, which are 3p and 7q. So, write them with a plus and a minus like this. At last, change these fractions to ratios. And finally, you have gotten the equation that you wanted to prove. And just like that, not only are you done with this lesson, but we're done with the Nando theorem family as well. Invertendo, alternando, componendo and dividendo. All of them. All that's left is practice on your part.